Okay, hello everyone. Welcome to my lecture on CIMC and CSMC, and thanks for supporting me. Okay, if any person could not come today, I will also record this meeting and I'll post it on my YouTube channel. Okay, let's start with CIMC. Hello. Um, okay. So let's start with CIMC question A5 and also have a PDF version of the contest. Okay, so question A5 is determine all pairs of x, y of integers with y is greater than or equal to x, for which 1 over x plus y 1 over y is equal to 1/4. Okay, so let's get into the solution. So 1 over x plus 1 over y is equal to 1/4. Now, this left-hand side is equal to x plus y over xy, and this is equal to 1/4. So then, if you cross multiply, you get xy is equal to 4x plus 4y, and then move this 4x and 4y to the left-hand side, which will get xy minus 4x minus 4y is equal to 0. And then, let me just copy this over. And then we could add 16 to both sides, which means we'll get and then factoring the left-hand side, which will get okay, since we know that x minus 4 and y minus 4 would be both integers, so let's consider a factor of 16. So 16 is equal to 1 times 16, 2 times 8, 4 times 4, -1 times -16, -2 times -8, and -4 times -4. Okay, now let's consider each individual pair. Since we know that y must be greater than or equal to x, then we also must have y minus 4 is greater than or equal to x minus 4, which means this number over here needs to be the smaller factor, and this number over here must be the greater factor. Okay, so now let's consider each individual case. So first start with 1 and 16. This means x minus 4 is 1 and y minus 4 is 16, which means you get one pair, which is 5 and 20. And then looking back, so the next pair is 2 and 8, which means x minus 4 is equal to 2 and y minus 4 is equal to 8, which means pair xy is equal to 6, 12. Okay, so the next pair would be 4 and 4. So 4 and 4. And they're equal. It doesn't matter which one equals to which. And we'll get a pair which is 8 and 8. Okay, so next pair is -1 and -16, which means it'll be -1, -16. Now this time, x minus 4 would be -16, and y minus 4 will be -1, which means xy would be -12 and 3. Okay, so 2 more pairs to go. Now it's -2 and -8. So -2 and -8, which means x minus 4 is equal to -8, and y minus 4 is equal to -2. Now you yield a pair that is -4 and 2. Okay, the last pair. -4, -4. -4, -4. So this time it would be x minus 4 is equal to -4, and y minus 4 is equal to -4. And this means x, y are 0, 0. Okay, now let's start checking over. So in this case, it will be 1/5 plus 1/20. And if you calculate it, that equals to 0.25, which satisfies. So this case is correct. And then next case will be 1/6 plus 1/12. And if you add them, you'll get 0.25, which means this is also correct. And then in this case, it will be 1/8 plus 1/8, which equals to 0.25, which means this pair is also correct. And this pair would be -1/12 plus 1/3. That equals to 0.25, no problem. So this one is also correct. And looking at this, it'll be -1/4 plus 1/2, and this equals to 0.25, which is good. Now, the last case, it'll be 1/0 plus 1/0. Since we know that we cannot have a 0 as a denominator, so this case is a failed case, which means we have 5 pairs of solutions. And there are 5, 20, 6, 12, 8, 8, -12, 3, and -4, 2. Okay, is everybody good with my explanation on question A5 on CIMC? Okay, I see a yes in the chat. Okay, Andrew, so what do you mean by where? Okay. Okay. Okay, Robert is asking for CIMC Part B, question 3, which I'll get to there right away. Okay, so next question I'll get into is question A6 on CIMC. Okay, so let's and I think most of you have know the question. So I'll just first read the question. So there are 90 players in the league. Each of the 90 players plays exactly one match against each of the other 89 players. Each match ends with a win for one player and a loss for the other player, or a tie for both players. Each player earns 1 point for a win, 0 point for a loss, and half a point for a tie. After all matches have been played, the points earned by each player are added up. What is the greatest possible number of players whose total score can be at least 54 points? And okay, let's consider at most there are X people with a score that is greater than or equal to 54. And since we want this X to be really, really big, then when these X people are playing against the other 90 minus X people, then we should let these people lose and these people win. So for each person in X, when they're playing against the other 90 minus X people, they'll get 1 point, which means this person has already got 90 minus X points. And then when each people is playing within X within this X people, let's say since we want them to be all of them to be greater or equal to 54, then we want them to be a tie. So each person within this X people will be playing against exactly X minus 1 people because you're not going to play against yourself, which means you get X minus 1 over 2 score plus 90 minus X. So each player in this X people will get this many points, and this score must be greater than or equal to 54. And the next step would be just solving this inequality. So it'll be X minus 1 over 2 plus 90 minus X is greater than or equal to 54. Now multiply by 2 on both sides, we'll have X minus 1 plus 180 minus 2X is greater than or equal to 108. And then over here will be negative X is greater than or equal to 108 plus 1, which is 109. So negative 71. And then we'll have X is less than or equal to 71. And which means there is at most 71 people with a score greater than or equal to 56. So our answer should be 71. So is everybody good with my explanation? So X is the number of people that is scored greater than or equal to 54. Okay, so I'm not seeing any person who are not good. Okay, so next I'll go for CIMC question B3, question D. And the question is, the integer a, b, c, d are equal to one of 1, 2, 3, 4, 5, 6, 7, 8, 9. And it is possible that two or more of the integer a, b, c, d have the same value. The integer p is equal to the product of a, b, c, d, that is p equals to a times b times c times d. So I think most people could solve part A and part B, which I won't do right here. So let's start from part C. So it wants you to find the number of possible different values of p that are divisible by 128 and not divisible by 1024. So, okay, so p is divisible by 128. However, p is not divisible by 1024. Now, 128 is equal to 2 to the 7th power, and 1024 is equal to 2 to the 10th power. So p is divisible by 2 to the 7th power. However, p is not divisible by 2 to the 10th power, which means p could be divisible by 2 to the 8th power as well, or p could be divisible by 2 to the 9th power as well. Okay, so let's consider each individual cases. If in this case, then p is not divisible by 2 to the 8th power, and in this case, p is not divisible by 2 to the 9th power. Okay, so first step is p is divisible by 2 to the 7th power, and p is not divisible by 2 to the 8th power. So looking back at the question, so A, B, C, D could be 1 through 9, and which means the most power of 2 is 8. So let's consider if this p is also divisible by 7. So p is divisible by 7. This means you must have a 7 in here, and you must have, and the rest, you must have 2 to the 7th power in it. And one of them must be an 8. Because if it's not an 8, then any other even number have at most power of 2 to the 2nd power, and 3 of them only gives you 2 to the 6th power, which does not satisfy. So one of them must be 8. And then we'll have these two slots open. And these two must produce a 2 to the 4th power. Now you could have 8, 6, or 4, 4, or 8, 2, which means these, just to watch out, because it is asking for how many different values of p there are. 7 times 8 times 8 times 2 is equal to 7 times 8 times 4 times 4, which means these 3 only produce 2 pairs. Okay, so that is when p is divisible by 7. And when p is divisible by 5, use the same method as 7. Really, is just changing this 7 to a 5. You also have, there are 2 solutions. And then, so now let's consider p is not divisible by 5, nor p is not divisible by 7. That means p is only divisible by 2s and 3s. So P would be equal to 2 to some power times 3 to some power. And 2 to the 7th power times 3 to the 0th power is achievable because you could have 2, 8, 4, 4. Oh, sorry. You have yeah, 2, 4. There we go. Yeah, this is achievable. And okay, let's consider how many 3s you can have at most. So you must have a 2 to the 7th power. And in order to have the most 2s, you should have 8. So say you have 8 and 8, and then you have 6, 9. In this case, it will produce 3 to the 3rd power. And as you can see, 3 to the 4th power is unachievable. So in this case, there are 3 could be to the power of 0, 1, 2, 3, which means there are 4 solutions. And adding all of them up, when P is divisible by 2 to the 7th power and not divisible by 2 to the 8th power, you'll get 8 solutions in total. Okay, so next step will be P is divisible by 2 to the 8th power and P is not divisible by 2 to the 9th power. Okay, use the same method. Say P is divisible by 7. Then you must have 7, 8, 8, and 4. In fact, there is no other solutions to P. There is only one solution. And for 5 is the same thing. You just change 7 to a 5, which means you'll also have one solution. And then next would be count how many when P is not divisible by 7 nor 5. Okay, so P would be 2 to the some power, 2 to the 8th power times 3 to the some power. Now 2 to the 8th power is achievable using 4, 4, 4, 4. And let's see how many 3s at most we can have. So we want the maximum number of 2s, then we'll have 8 and 8. And we could have 4, 9. In this case, you have 3 to the 2nd power, or you can have 6, 6, which is also 3 to the 2nd power, which means 3 could be 0th power, 1th power, and 2nd power. Which means there are 3 solutions in this case. And adding them up, we'll have 5 solutions. And then, so the last case, which is P is divisible by 2 to the 9th, and P is not divisible by 2 to the 10th. Same method. When P is divisible by 7, you'll have 8, 8, 8, 7, which yields one solution. When P is divisible by 5, there'll be 8, 8, 8, 5, which yields one solution. And then when P is not divisible by 7 nor 5, we'll have P is equal to 2 to the 9th power times 3 to the some power. 2 to the 9th power is achievable using 4, 4, 4, 8. And now let's look at how many 3s we can get at most. So you can have 8, 8, 8, 9. And which means this could be 3 to the 2nd power, which means you have 0, 1, 2th power, which means you have 3 solutions in this case. And In this case, we'll have 5 solutions in total. So in total, we have 5, 5, and 8. Adding them up, we'll have, so this is a 8, this is a 5, this is a 5. Adding them up, we'll have 18. So there are 18 solutions, 18 possible different values of P that are divisible by 128 and not divisible by 1024. So is everybody good with my solution here? Okay, so then let's look at part D. Part D is determine the number of ordered quadruples, noticed as ordered quadruples, and is wanting you to find ABCD, not P, for which P is 98 less than a multiple of 100. Okay, so we have P is 98 less than a multiple of 8, a multiple of 100, of 100. This means P is negative, is congruent to negative 98 mod 100, which means P is congruent to 2 mod 100. In other words, P is 2 more than a multiple of 100. Okay, so we know that P is congruent to 2 mod 100, mod 100. Notice that 100 is 4 times 25. So when P is congruent to 2 mod 100, this means that P is congruent to 2 mod 4, and P is congruent to 2 mod 25. Okay, so looking at first piece of information that we got, this means that P is a multiple of 2. So P is a multiple of 2. However, P is not a multiple of 4. What this tells us is the product of ABCD is only a multiple of 2, not a multiple of 4, which means we cannot have 4, we cannot have 8, and only one of ABCD is a power of 2. I mean 2 or 6. So let's just consider one of which is, let's consider one of them is a 2, so case 1. There is a 1, there's a 2, is a 2. And then we can know that P is equal to 2 BCD, say A is 2. And then we could rearrange them and find how many numbers of solutions there are. And now BCD are not multiples of 2, which means BCD could only be 1, 3, 5, 7, and 9. Now we know that P is congruent to 2 mod 25. Then we'll have BCD is congruent to 2. Sorry, congruent to 1 mod 25 because you divided by 2. Okay, so 25 is a multiple of 5, and BCD, when multiplied together, their product is not a multiple of 5, which means BCD cannot be 5. So BCD could only be from 1, 3, 7, 9. Okay, now there is no other better solution for trying all of them. So let's say B is equal to 1. B is equal to 1. That means CD, let's write it over here. CD is congruent to 1 mod 25, which means CD must be 1, 1. And when B is equal to 3, CD is congruent to, it'll be congruent to 17 mod 25. Just a quick question. Does anyone know why CD is congruent to 17 mod 25? So I assume that is no question. So then let's move on. Now remember CD could be only 1, 3, 7, 9. And this is unachievable, so no solution. And when B is equal to 5, you can't be 5. B is equal to 7. CD is congruent to, this would be, let's see. So CD will be congruent to 18 mod 25. Again, this is unachievable. And now when B is equal to 9, we'll have CD is congruent to 14 mod 25. So it only could be 1, 3, 7, 9. Once again, this is unachievable. So in this case, when there is a 2, we get 2, 1, 1, 1. And since this is an ordered quadruple, then you can have, there are 4 solutions, 4 sets. Oh, let me just write it in another color. So there's 4 solutions in this case. There is 1, 2. Now, case 2, it would be, there is a 6. There is a 6. So in this case, so it'll be P is equal to 6 times BCD, which means P would be congruent to 17 mod 25. And when b is equal to, and then keep trying all of them. Oh, I can't add a new slide. Okay. I guess we'll have to clear something. Okay, so when b is equal to 1, that means CD is congruent to 17 mod 25. And this is unachievable. When b is equal to 3, this means CD is congruent to 14 mod 25. Once again, this is unachievable. Now, when b is equal to 7, this means that CD is congruent to 6. Now, there is a solution in this set, which is C and D are both equal to 9. So 9 times 9 equals to 81, which is congruent to 6 mod 25. So we get one solution in this set. And then next up, B is equal to 9. That means CD is congruent to 13. 13 mod 25. This is also achievable because you can have C equal to 7, D equals to 9. That equals to 63, which is congruent to 13. Now, looking at this is 799, this is 979, which means these two pairs give the same pair of solution, which means here it'll be 9976. And in this case, there are 12 solutions for quadruples A, B, C, D, which means 12 and 4 added together, there are 16 cases in total. And there we go. We got the answer. So there are 16 pairs of ordered quadruples. So is everybody good? What's the solution? Okay, so I see a request for part B, question 2B. I'll get into CSMC first, and then I'll come back to this question. So what I would do would be, okay, so I'll first do question 5 on CSMC. Now I have to clear something. Okay. Okay, I think that's enough. So we have 3 times sine x plus 4 times cosine x equals to 5. So 3 times sine x plus 4 times cosine x, 4 times cosine y, sorry, equal to 5. And 4 times sine y plus 3 times cosine x. So 4 times sine y plus 3 times cosine x is equal to 2. And it wants you to find sine x plus y. So sine x plus y. And now there's a fact that is sine x plus y is equal to sine x cosine y plus cosine x sine y. I'll also write that in here. So that is equal to sine x cosine y plus sine y cosine x. Now looking at this, you could just square these two and there will be some product, which probably will satisfy here. So let's just square them. So the first one will be squared would be 9 sine squared x plus that'll be 24 sine x cosine y plus this will be 16 cosine y, cosine squared y is equal to 25. And squaring the second equation, we'll get that'll be 16 sine squared y plus 24 sine y cosine x plus 9 cosine squared x is equal to 4. Now, notice that there is a 9 sine squared x and 9 cosine squared x and 16 squared sine squared y and 16 cosine squared y. So we could just add them, which means these two, which means the two part in red circle added together is a 9 plus the two part in yellow circle would be 16 plus, now the rest would be just 24 times sine x times cosine x, cosine y plus sine y cosine x. That is equal to 29. Now looking back, that is sine x plus y. So which means we'll get 25 plus 24 sine x plus y is equal to 29, which means 24 sine x plus y is equal to 4, which means sine x plus y is equal to 1/6. And there we go, we have our answer. So is everybody good with my solution on A5? Okay, so let's then move on to question A6 on CSMC. And for this question, it'll be definitely tougher. Okay, so let's write the few rules. So f1 minus x is equal to 1 minus fx. So f 1 minus x is equal to 1 minus fx. And f 1/3 x is equal to, oh, so f 1/3 x is equal to f 1/2 f of x. And the third rule would be f is strictly increasing. So I would just leave it there. So first, we could calculate f0. So using the second rule, so f 1/3 times 0 is equal to 1/2 times f0. Now 1/3 times 0 is 0, which means f0 is equal to 1/2 of 0, which means 1/2 of f0 is equal to 0, which means f0 is equal to 0. So then we could find f1 using the first formula. So f1 minus 0 would equals to 1 minus f0, which means f1 equals to 1. And then use the second rule again. So f 1/3 times 1 is equal to 1/2 times f1, which means f 1/3 is equal to 1/2. And then use the second rule again. No, use the first rule. So it'll be f1 minus 1/3 is equal to f minus f 1/3. Which means f 2/3 is equal to 1/2. Now looking at these two values, we'll notice that since we know that when b is greater than or equal to a, f of b is greater than or equal to f of a, this means anything in between 1/3 and 2/3 will all equal to 1/2. So which means when x is greater than or equal to 1/3 and x is less than or equal to 2/3, then fx is equal to 1/2. Now, when x is equal to 3/7, this is between these two numbers, which means f 3/7 would be equal to 1/2. Now, use the second rule, which is the f 1/3. f 1/3 times 3/7 is equal to 1/2 times f of 3/7, which means f1/7 is equal to 1/4. Now we know that f1/7 is equal to 1/4. Then we can know that f of 1 minus 1/7 is equal to 1 minus 1/7, which means f6/7 is equal to 1 minus 1/4, which is 3/4. And we have found our answer of f6/7, which is 3/4. So is everybody good with question A6? Okay. Okay, so we're plugged in. Okay, so we know that f1/3 is equal to 1/2, and f2/3 is equal to 1/2. Yeah, no problem with this, right? And by third rule, that tells us when b is greater than or equal to a, then f of b is greater than or equal to f of a. Now what this means is that you let b equal to 2/3 and a be any number between them, and we must have fa is less than or equal to 1/2 by here, and fa is also be greater than or equal to 1/2, which means fa is equal to 1/2. Okay, yeah, that makes sense. Okay, anybody else have any other questions? Okay, so let's then go to CIMC question B2 part B. I think I'll just do my solution down here. So initially, tank C is full of water and tank D is empty, and tank D begins to fill with water at a rate of 1 centimeter cube per second. And 2 seconds after tank D begins to fill, tank C begins to drain. So let's say T second after tank D starts to fill. So T second after tank D starts to fill, there will be T times 1 amount of water in tank D, and in tank C there will be, initially it is full, which means there's 4 times 31 times 4 centimeter cubed amount of water in there, which is 496. centimeter cubed water in tank C. So tank C starts 2 seconds after tank D starts to fill, and tank C starts to drain, which means after T second tank D starts to fill, tank C will have 496 minus 2T minus 2. There will be this amount of water after T second. And simplifying this, we'll have that equals to 500 minus 2T. And it says at one instant, the volume of water in tank C is equal to the volume of water in tank D. So that happens when 500 minus 2T is equal to T, which means T is equal to 500 over 3. So at this time, it wants you to find the depth of water in tank D. So there will be T times 1, which means there will be 500 over 3 centimeter cubed amount of water in tank D. And this means that if it will fill up to some place, say it will fill up to here. And say the depth is D. Now from the description of tank D is 10 centimeter. The height of the tank D is 10 centimeter, and the side length of the square base is 20 centimeter, which means this base is twice as much as the depth, which means when you're at depth D, the side would be 2D. So the volume of water when there's a depth of D would be, so the base square would be 2D squared times the height, which is D, times 1/3. And this is 4 over 3 D cubed. And at this instant, since there are 500 over 3 centimeter cubed water in there, then we will have D cubed is equal to 125, which means D is equal to 5 centimeters. So the depth would be 5 centimeters in tank D. So is everybody good with this solution? Okay, I think that's a yes. So anybody else have questions on the other questions in this contest? In both CIMC and CSMC? CSMC and CIMC contest. I have the PDF version of it, but I don't think the contest is released online. Okay, so B3 on CSMC would take really long. Do you still want to listen to B3 on CSMC? Okay, I guess. B3. Okay, so this question, okay, we have to start with part B because if you did not do part B, you cannot do part C. I will just walk through part B on here and part C probably on whiteboard. So P must be a multiple of 3. Okay, so P must be a multiple of 3. So by Vienna's formula in G, so x1 plus x2 is equal to 2p over 3. We know that x1 and x2 are integers. It says right here. It has 2 distinct integer solutions. This means 2p over 3 is also an integer, which means 3 is a multiple of 3. So this is proved. So now for Q. So first, by Vienna's formula again in here. So x1 multiplied by x2 is equal to q over 3, which means q is a multiple of 3. So we have q is a multiple of 3. And then use Vienna's formula again in f. So one of the root of f is x equal to 0. So let h of x equal to x squared minus px plus q. So in here, in hx, x1 times x2 is equals to q. Since q is a multiple of 3, what that tells us is one of x1 and x2 is a multiple of 3. So without loss of generality, let x1 be multiple of 3. And by Vienna's formula again, so in h of x, x1 plus x2 is equal to p in here. So we know that p is a multiple of 3. And that means x2 is equal to p minus x1. So both p and x1 are multiple of 3. That means x2 is also a multiple of 3. And we know that q is equal to x1 multiplied by x2, and both of which is a multiple of 3. This means q is a multiple of 9. So the second part is proved. And let's leave this hx here. And then, so for number 3, it'll be by quadratic formula. So by quadratic formula in G, x is equal to 2p plus or minus square root of 2p squared minus, this would be 12q over 6. So this part right here must be a perfect square, which means 4p squared minus 12q is a perfect square. And that is equal to 4 times p squared minus 3q. Since this is a perfect square, that means this must be also a perfect square, which means this has to be a perfect square. So part 3 is proved. Now part 4. Oh, I should not erase that. So part 4, it'll be by quadratic formula in h of x. So in h of x, x would be equal to p plus or minus p squared minus 4q over 2. And this part must be a perfect square, which means this is proved. So now part B is proved. Okay, so if we want f to have 3 distinct integer solutions, that means h has 2 roots. So in here, even if this is a perfect square, but if the top is a odd number, that does not satisfy. So if p is a odd number, so it'll be an odd number plus or minus. P squared will be an odd number, and p squared minus 4q would be also an odd number, and the square root of an odd number would be also an odd number. So it will be an odd number plus or minus another odd number, which means the top will be definitely an even number. So in this case, x is an integer, that is no problem. Now looking at this part right here, so we know that both p and q are a multiple of 3. Oh, you know what? I could actually simplify this even further. So x is equal to, if you divide by 2 on both top and bottom, we'll have that equals to p plus or minus square root of p squared minus 4q over 3. We know that both p and q are a multiple of 3, and q is a multiple of 9. P squared will be a multiple of 9, and negative 4q is a multiple of 9, which means the part in square root is a multiple of 9, which means the part after plus or minus is also a multiple of 3. So this is also integer, which satisfies. So what this tells us is if PQ satisfy all these 4 conditions, that means F have 3 distinct integer solutions, and G has 2 distinct integer solutions. And part C is just prove that there are infinitely many pairs of positive integers P and Q for which the following 3 statements are true. Now these 2 statements are equivalent to these 4 statements. And really it just adds another statement, which is the common divisor of PQ is 3, which means GCD PQ is equal to 3. Okay, so I will do part C on whiteboard, and I need to clear something. So that's probably enough. So we must have P is divisible by 3, Q is divisible by 9, P squared minus 3Q is a perfect square equals to A squared. P squared minus 4Q is also a perfect square, say equals to B squared. And GCD PQ equals to 3. So let P0 3P0 equals to P, which means P could be not, P0 could be not a multiple of 3. So, and 9Q0 equals to Q. And now looking at this satisfied? Since P0 and Q0 must be an integer, so these two conditions are now satisfied. And then looking at these two right here, so it'll be 3P0 squared minus 4Q0. And when you, oh, sorry, that 4 times 9 times Q0. Now when you expand this, you'll have 9P0 squared minus 4Q0. This means that P0 squared minus 4Q0 is also a perfect square. And if you do the same thing, you have to this, you'll have the same result. You'll have 9 times P0 squared minus 3Q0 squared. So these two numbers must also be a perfect square. Now looking at the last condition, which is GCD of 3P0 and 9Q0 is equal to 3. What this tells us is that P0 and 3Q0 has only a common factor of 1. So really, the 3 conditions that we right now need to satisfy, which are P0 squared minus 4Q0 is equal to a squared, with say A squared, and P0 squared minus 3Q0 is equal to B squared. Now these are the 3 conditions that we need to satisfy. So let's circle them. And then rearranging these two, we'll have A, 0, okay, so A minus P0 multiplied by A plus Q0, P0 is equal to 4Q0. And B minus P0 times B plus Q0 is equal to 3Q0. Oh, sorry, this is a P, this is a P, this is a P. So, okay, so let this equal to X, let this equal to Y, let this equal to W, let this equal to Z. So we'll have hang on, is that? oh, sorry about that. It should be P minus, should be P0 minus A, and so on. This should be this should be P0 minus A, not A minus P0. And P0 plus A, and P0 minus B, P0 plus B. Yeah, that is correct. Okay, so let X equal to P0 minus A and Y equals to P0 plus A and so on. So now you have X plus Y is equal to 2P0. Also, W plus Z is also equal to P0, 2P0, which means X plus Y is equal to W plus X. Also, in this equation, this is the same as X times Y equals to 4Q0. W times Z is equal to 3Q0. Since we know that these two sum are the same, but X times Y is greater than W times Z, that means if you plot them on a number line, oh, that's a terrible line. If you plot them on a number line, it'll be say this is X, this is Y. That means W and Z are outside of X and Y, and this distance are the same. So let this distance be K. So then we'll have X minus K is equal to W, and Z is Y plus K. Now that is W times Z, which equals to 3Q0. Now, which means, so 4X minus K times Y plus K, that equals to 12Q0, right? And looking at this, X times Y is equal to 4Q0. That means 3XY is equal to 12Q0, which means these two terms are the same. So expand the top equation, you'll have 4XY minus 4KY plus 4KX plus minus K squared is equal to the bottom, which is 3XY. And then simplifying this, you'll have, well, let's change the color. XY minus 4KY plus 4KX minus K squared is equal to 0. Really? Oh, sorry, I just made another mistake here. This should be minus 4K squared. Okay, so that'll be still minus 4K squared. There we go. This means that XY minus 4KY plus 4KX minus 16K squared is equal to negative 12K squared. What this means is X minus 4K, Y plus 4K is equal to negative 12K squared. Okay, so now what I did is that plug in some numbers. When k is equal to 1, this means x minus 4 times y plus 4 is equal to negative 12. Now, this term could be negative, however, this term cannot. So let this be negative 2, and this is be positive 6. So it'll be 2 and that 2 and 2. And this means that P0 is equal to 2 and Q0 is equal to, what is Q0? Q0 is W times X divided by 4, which is 1. Now this satisfies, because when P0 squared minus Q, 3Q0 you get 1, and Q0 squared minus 4Q0 you get 0. That also is a square, and the greatest common factor is 1. So this solution satisfies. And then when k is equal to 2, that means x minus 8 times y plus 8 is equal to negative 48. So once again, this number could be a negative number. This cannot. And let this to be negative 2 and this to be 24. We'll get x is 6, y is 16, which means P0 is 11, Q0 is multiply and then divided by 4 is 24. Checking the solution, this also satisfies. This pair of solution also satisfies. Now, look at these negative 2. What I noticed is that if this term is equal to negative 2, and this term is equal to 6k squared, this is likely going to satisfy. So this means that x is equal to 4k minus 2, 4k minus 2, and y is equal to that'll be 6k squared minus 4k. 6k squared minus 4k, which means P0 is equal to adding them together and divided by 2, which is 3k squared minus 1. Q0 is multiplying them together and then divided by 4. So first, divided by 2 on both of these, you have 2k minus 1 multiplied by 3k squared minus 2k. Factoring out a little bit, take this k out and move this k a little bit over, I guess. So Q0 is equal to this. And this satisfies. This satisfies these two. Now, there is only one condition left. If this pair of solutions satisfies this, then this solution is valid, which means we're done. So we must prove that GCD of P0 and 3Q0 is equal to 1. Okay, looking at this, P0 and GCD of P0 and 3 is equal to 1 because this is a multiple of 3 minus 1, which is definitely not a multiple of 3. Okay, oh, gotta clear it more. Okay, I think that's enough. Okay, so now let's prove that P0 and Q0 does not share any common factors. So these two terms does not share any common factors because this is 1 less than a multiple of k. And now let's look at, so which means GCD of P0 and k is equal to 1. Now look at 3k squared minus 1 and 3k minus 2. Now the greatest common factor, let's find the greatest common factor. So this is equal to 3k minus 2 times k. Times k, that will be plus 2k minus 1. Now, the greatest common factor between these two terms is equivalent to the greatest common factor between 2k minus 1 and 3k minus 2. Now, we know that the greatest common factor of any two consecutive numbers are 1. So 6k minus 3 and 6k minus 4. The common factors between them is 1, which means these two, now this divided by 3 is that, and this divided by 2 is this, which means these two numbers have a greatest common factor of 1. So GCD of P0 and 3k minus 2 is equal to 1. Okay, so just one term left is now 3k squared minus 1 and 2k minus 1. So 2k minus 1. Okay, so this term is equal to k times 2k minus 1 plus k squared plus k minus 1. And this is 2k minus 1. Okay, so saying to find the greatest common factor of these two is equivalent to finding the greatest common factor of these two. Now, this term is k times k plus 1 minus 1. Is it? Yes, I think it is. So 2k, hang on. Plus, yeah. So 2k minus 1 and 2k has a common factor of 1. So these two terms have a common factor of 1. And 2k minus 1 and this and 2k plus 2. And we know that, and hang on, so whatever. This is 2k squared plus k squared minus k plus k. Yeah. And oh, this is not what I did. So now you need to subtract it also by 2k plus 1. That is equal to k times 2k minus 1 plus 2k minus 1 plus k squared minus k and 2k minus 1. So saying to find the greatest common factor of these two terms is the same as to find the common factor of these two terms. So we know that k squared minus k is k times k minus 1. And when you multiply both of them by 2, you have 2k and 2k minus 2. And both of them are exactly 1 apart from 2k minus 1, which means all of them are related prime, which means these two have a greatest common factor of 1, which means GCD of P0 and 2k minus 1 is 1, equal to 1. Now here, of all that I said, this means GCD of P0 and 3Q0 are have a greatest common factor of 1. And which means for every integer of k, this will satisfy, which means there are infinitely many P0 and Q0, which means there are infinitely many P and Qs, so that they satisfy all 5 statements. Okay, so we could plug in a few numbers if you want. So when k is equal to 1, we already found that P0 is equal to 2, I think. Yeah, 2 and 1. 2 and Q0 is equal to 1. And this means that P is equal to 6 and Q is equal to 9. And when K is equal to 2, that means P0 is equal to 11. And Q0 is equal to 24. And this means that P is equal to 36. And Q is equal to 216. Oh, sorry, this is 33. Which is what we had in part A, and so on. If you just continue, you have infinitely many PQs, and that is the proof. Okay, I think that will be good for this session, and hope you guys have learned something.